Okay, this PowerPoint is over the chi-square and pedigree from Chapter 3. Chi-square analysis is used to determine how well the observed values fit the expected values. This can also be called the goodness of fit test. It indicates that the probability that the difference between observed and expected is due to chance. Some important terms are the degree of freedom, which is n minus 1, where n equals the number of expected phenotypes. This is the formula for the chi-square analysis. X squared equals the sum of the observed value minus the expected value squared over the expected value. This is the chi-square table that we're going to be using for problems 1 and 2. Up here is P. This is the degree of freedom. So problem number 1. When crossing two homozygous parents, dominant purple flower with recessive white flower, F1 generation is formed, get all purple flowers. Self-fertilization. The F2 generation, which is right here, is expected to demonstrate 3-to-1 phenotypic ratio. Right here. 3/4, 1/4. The observed ratio is 105 purple flowers to 45 white flowers. We can use the chi-square analysis on this. First, we have to find the chi-square value. So we take the 105 minus the observed minus the expected squared over the expected plus observed minus expected squared over the expected. And to sum this up, x squared equals 2. That is our chi-square value. The degree of freedom is n minus 1. N being purple and white, so 2 minus 1, so the degree of freedom is 1. We can see here, degree of freedom is 1. The value is going to be between 2 and is 2, which is going to be between 0.5 and 0.1. So there's no significant difference between the observed and expected values. Problem 2. So in corn, purple kernels are dominant over yellow, full dominant over shrunken. A corn plant with purple full kernels is crossed with a yellow plant that is shrunken kernels. So these are our observed values. The parents are most likely going to be purple full, P, P, F, F, crossed with yellow, lowercase p, P, F, F. You can see this here, these are our results. So these are the observed results we saw previously. Expected is 100 of each. So if you do the analysis for each individual color, our value is 2.7. If we look again, if we go back, the degree of freedom is going to be purple full, purple shrunken, yellow full. So 4 minus 1 is 3. So the degree of freedom is 3 over 2, our p-value of 2.7. So 3 over to 2.7 is going to be between 0.5 and 0.1. So there's going to be no significant difference between the observed and expected values. Problem 3. Joanna has short fingers. This is her family history here. She has twin brothers with it. Okay. Mode of inheritance for short fingers in this family. This is their pedigree. This is Joanna right here, married to Tom right here. These are Joanna's twin brothers and her other 2 sisters. We can see that this is autosomal dominant because it appears in both sexes equally with equal frequencies, and there is no skip in the generation. So this child is adopted. These are Joanna and Tom's other 2 children. a girl with short fingers, a boy without short fingers. They were to have a third child. What is the probability that they will have short fingers? We know that Joanna is going to be heterozygous because her mother does not have short fingers and her father does. And we know that Tom is going to be homozygous because there's no family history of the short fingers. So when you cross these two, there's approximately 50% of their chance their children will have short fingers. So we can see right here that 1/2 probability that the child will have short fingers is going to be 1/2. So accept.